My topic today is about carbon capture, and I work primarily in the United States. So today's presentation will mostly be a discussion about my experience in carbon capture in the United States. The technology is being considered worldwide, and so I think most of the matters and the issues that we'll discuss today are applicable to a project regardless of where it's located, but just wanted to make that initial disclaimer. Okay, so a bit about me. I worked in the power industry in the United States for 40 years, and I developed a number of power plants in my career. And then toward the end of my career, I was asked to look at developing a carbon capture project on one of my company's coal-fired power plants. President Obama had just been elected, and the feeling was that climate was going to be a bigger emphasis for the administration. And so the company that I worked for had many coal-fired power plants, and we needed to find a way to reduce carbon emissions so that these plants could continue to provide the valuable service of reliable and affordable electricity to our customers. So in 2009, I started a project called Petronova, and at the end of 2016, Petronova came online and was on time and on budget. So that's why I'm here. The project received a lot of attention internationally, and so I hosted over 200 tours from people inside the United States and from outside, and I've made over 80 presentations on this project. So what I'm going to talk about today is more about the next wave of projects after we take into account the learnings from the Petronova project. So why do it at all? Why do carbon capture? And it's my belief that those of us in the industrialized nations have benefited greatly from the use of fossil fuels. It's a high energy density fuel. It's very reliable. We know where it is. We know how to get it. And we can count on it to keep our factories running, the lights on, our agriculture producing, all these things. So it's incumbent on us as the world moves more to a carbon neutral energy infrastructure. It's incumbent on us in the industrialized nations to figure out how to continue to use this fuel but reduce its environmental impacts. So as we talk about carbon capture, one of the very first things that we need to think about is the technology ready? Are we at a point where the industry is ready to launch? And so for those that haven't been a part of a demonstration project or a cutting edge technology, the U.S. Department of Energy funds projects that are in the lab scale, and then they also fund major demonstrations. And usually the major demonstrations are for projects that are not quite proven commercially, but are ready to be proven commercially. All the scale-up issues have been dealt with, all the ongoing industrial, round-the-clock operational issues have been dealt with, and now the technology is ready. To kind of capture where projects are and where technologies are, there is a scale called the Technology Readiness Scale, or level. And TRL indicates where you are. Generally, commercial banks and lenders and investors will only invest in TRL 9 technology. Some that are more leading edge will, if they're given an interest in the technology, they will go lower down in the technology level readiness. So you can see some projects that are only at a 7, for example, that get built and invested in. But these investments generally come with ownership of the technology because they're helping to bring the technology to that TRL 9 level. Today in our industry, our CCS industry, there are very few technologies that are at TRL 9. There are more that are in the TRL 7 and 8 category, and then there are many in the 5 to 6 category. So depending on what the project is trying to accomplish, are we trying to develop a commercially viable carbon capture system, or are we in the process of moving up the TRL scale? Today, really, I've only seen banks and large institutional investors willing to invest in liquid amine. There are other technologies that are getting close to the TRL 9, but right now, liquid amine is really the only technology that for large-scale carbon capture projects is ready. This TRL concept applies not only to capturing carbon dioxide, because as you can imagine, capturing CO2 is only one half of the equation. What do you do with it after you've caught it? You have to put it away somehow. And there are many ideas on how to use the CO2. The problem with those technologies is every single one of them, whether you're talking about algae converting, using sunlight and algae and photosynthesis to turn carbon dioxide into usable products, whether it's chemical looping to turn carbon dioxide into petrochemicals or into fuels. All of those uses, the U in CCUS, all of those uses suffer from the same problem as volume. And when you look at the scale of the carbon dioxide emissions that need to be dealt with, the uses that are emerging that people are investing in are novel, they're interesting, they're nice, but they're not going to move the needle on a global scale. Today, really only the geologic storage, whether it's in a saline reservoir, displacing salt water out of the formation and putting carbon dioxide in its place, or using carbon dioxide in enhanced oil recovery. These are the only two methods of storage that we have that are capable of handling the volumes that will actually move the needle on our ability to decarbonize our energy industry. There's a couple of notes to think about when you think about TRL level. The TRL makes no judgment as to the actual CO2 emissions reduced. So there are many ideas about how to reduce CO2. Some of them are more advanced than others. But the TRL is the technology commercially viable? It doesn't say whether it's effective at removing carbon. And also, the TRL does not consider life cycle analysis. So just because the liquid amine process is at TRL 9, that doesn't mean that every ton you capture in your liquid amine system results in a net ton removed from the atmosphere. So keep those in mind as you think about which technologies are being considered for projects. So as I mentioned, the liquid amine technology is really ready for commercial deployment at industrial scale. By industrial scale, I mean a single train. These days, for most of the liquid amine manufacturers or technology owners, 4 million, 4.5 million metric tons per year size range. That's the equivalent of about a 500 megawatt coal-fired power plant. That's where the state of the technology is. The cryogenic technologies certainly are at TRL 9, but to date have proven to be a little costly and tend to be more of a smaller scale application than what we see with liquid amine. There are other technologies that are getting close. Solid adsorbents, Savante I've got on the list here. They have a unique technology for, if any of you are familiar with how air preheaters work in industrial process like a power plant. It's a very large wheel, and they put these cartridges of solid amine impregnated filters that catch carbon dioxide as the wheel moves through the flue gas, and then it regenerates as it makes its circle. It's being tested on cement right now. There's 2 projects, one in Vancouver and one in Colorado in North America. And so it's proving to be a very viable possibility. Their membranes, these are filters basically that are engineered and designed to exclude carbon dioxide and let nitrogen and oxygen pass through. These are already industrial, but they suffer from some issues with purity. The selectivity of the membrane to only prefer carbon dioxide is still not quite there. You get not quite the purity, or if you go for the high purity, you end up missing a lot of carbon dioxide. So they're running that balance between high purity product out of the product side of the membrane versus how much carbon dioxide you're willing to let bypass your filter. So they're wrestling with that. There's a company called MTR, Membrane Technology and Research. They're in California in the United States, and they sell a lot of membranes for industrial applications, and they're just now proving out their carbon dioxide membrane. Then there's the direct air capture. This gets a lot of attention. I certainly have my opinions about which CO2 emissions should be prioritized with the limited funds that each nation has to invest in this. But many people are excited about this. This is an opportunity for airlines who it's almost impossible for them to abate their carbon emissions or prevent carbon emissions from an airplane. So instead, they invest in this technology known as direct air capture, where you literally set up over your storage field and pull in air and remove carbon dioxide from the atmosphere directly, and then store the CO2 geologically below the plant. This is very expensive right now, and as we'll talk about in a little bit, though, there's great hope that as more and more of these units are built, just like with valve manufacture, the more you build, the better understanding you have of how to manufacture and how to build these things, and you solve problems as you go. So direct air capture is close. There are a few operating units around the world, and there are many more planned. I believe Occidental Petroleum is planning the world's largest in the Permian Basin region of Texas in the United States. So it'll be a 1 million ton per year project. So you can see the largest in the world will be 1 million tons, and we already have amine capture systems that can capture 4 million tons per year. So then there's the utilization. Where are we with those? There's mineralization. There was at one time a lot of hope that there were certain rocks in the ground that you could pump carbon dioxide into, and very quickly the carbon dioxide would turn into a carbonate, a mineral, and therefore be permanently sequestered, not in a gaseous state or a liquid state, but in a solid state. There are many technologies out there, Fischer-Tropsch-based technologies that look to use catalyst and pressure and temperature to manipulate the carbon dioxide molecule back into a useful product like a petrochemical or a fuel. And then, as I mentioned earlier, algae. These are all making their way up the TRL scale, but again, even when they make it, it's my opinion that they're going to suffer from not being able to handle the volume. At one time, when we were developing Petronova, we did a quick look at the possibility of sequestering the carbon dioxide that we were going to capture in cement. A lot of concrete being used for road buildings in Texas where the plant was. And we figured that we would be able to pave the entire state of Texas in 3 years with the emissions from that plant with 4 inches of concrete. So it's a good way to dispose of carbon dioxide. It's just not a high volume means of disposing. As I mentioned earlier, with any technology, we see a curve, and the curve varies depending on the technology and depending on the investment and the interest in accelerating the advancement on this curve. But costs do come down over time as people get experience with building and operating a technology. The technology gets lower in cost to build and to operate. This is an example of 4 different classes of photovoltaic solar, from residential on the left to utility scale on the right. And you can see that over the last 8 years, the cost of the technology has come down dramatically. And so I do get a lot of questions about why bother to do carbon capture, because the technology is so expensive. And I just remind them that wind and solar 10 years ago were prohibitively expensive as well. And as you can see from these charts, the costs have come down as we've built more and more units, as we've installed them, as we've gained experience with them in the field. We figured out ways to make them better and better over time. So it's no reason to believe that with carbon capture, as we build more and more copies, that we will see that same cost curve. Okay, so for many people in this room, we're interested in carbon capture because you're getting requests for quotes. People are doing feed studies on carbon capture systems. There's low pressure parts of the carbon capture technology. There's high pressure parts. There's carbon dioxide, corrosive. There's many factors to be considered. So how do you decide which projects to pay attention to and to make your best proposals for? So I'm going to talk a little bit about the economics of carbon capture, what's driving it, so you can make judgments on the projects that come before you. So when we're talking about processing flue gas, this is the idea that we're going to catch the CO2 before it gets in the atmosphere, while there is still some significant concentration. As with any mining operation, and you can think of carbon capture as mining, the richer the ore that's coming into your process, the lower the cost is to build a facility to process it. So I think I saw that there are 6 rivers in China that account for 80% of the plastic that's floating in the Pacific Ocean. And so rather than the efforts that are underway now to go out into the Pacific and find this plastic and collect it, if we just were able to catch it before it comes out of those rivers, it'd be much more cost effective than searching the oceans for plastic bottles. Same concept here. We're talking today about capturing carbon dioxide at the emission point where there is a high concentration of CO2 and it makes sense to do that. So as you can imagine though, the richness of your ore, of your raw material, in this case flue gas, is directly proportional to the cost to build the facility to capture your carbon dioxide. So I apologize for the acronyms here. NGCC stands for Natural Gas Combined Cycle. This is combustion turbines with heat recovery boilers on the back, power plants, and they're fueled by natural gas. These things are very efficient, which makes them very desirable. But if you're trying to capture the carbon dioxide from these units, it's a challenge because they're so efficient. There's only 3% CO2 in the flue gas. A boiler is a little less efficient, very intuitive, and likewise has a higher concentration of carbon dioxide. Coal, just because of the nature of burning a solid fuel, ends up with a even higher concentration. Cement, you get carbon dioxide from 2 sources. First, the heating up of the clinker, usually with natural gas or some other fossil fuel, that has about an 8% concentration. But then the actual calcination of the rock, of the limestone, gives off trapped carbon dioxide, and that stream is more like 20 to 22%. So the average is around 16% of the flue gas coming out of a cement plant, and makes it a very desirable place to put a carbon capture project. And then finally, hydrogen steam methane reforming, SMR. If you're familiar with the chemistry in that process, there's, in some cases, depending on which process you're using, you have pure CO2 coming off of the unit, but in many of the legacy SMR plants, you end up with a blend of several streams that average out to about 22% carbon dioxide. And this is important. The reason I bring this up is the cost to build, the capital cost to build a carbon capture system is driven by the volume of flue gas that you're treating, not the carbon dioxide you're going to capture. And I'll just say that again. It's the cost to build the facility is driven by the amount of flue gas you're going to process, and not by the concentration of the CO2. In working with some engineering firms in the U.S., a rule of thumb is it's around $9,000 per ton per day of flue gas to build a gas processing system. And so if that's a fixed number, then obviously the lower concentrations are going to be higher in cost per ton of actually captured carbon dioxide. So for a lot of folks, this isn't intuitive. They think the bigger you build a plant, the more carbon dioxide you capture, the more expensive it's going to be, and that's not necessarily the case. Okay. Operating costs, though, are strictly driven by physics. The liquid amine system is a temperature swing absorption. The amine molecules that are in the solvent that runs around in an amine system is designed with a chemical socket that at low temperatures CO2 plugs into. Actually, there's an affinity there, jumps into, and so you have to bring the liquid in contact with the gas, and every time a CO2 molecule bounces against an amine molecule, it sticks at low temperature. But the bond is thermally unstable, and so in order to release the CO2, we move the amine to a regenerator and heat it up. So a lot of the cost to capture carbon dioxide is driven by electricity to run solvent back and forth between the two vessels that are in these systems, the heating of the solvent to get the release, the cooling to get the CO2 to stick in the first place, and then what I call liquefaction, a lot of people call compression. It's basically turning the atmospheric pressure carbon dioxide into supercritical fluid. Usually you see pipelines for carbon dioxide in the U.S. operated at about 1,800 psi. I'm sorry, I don't know how many bar that is, but in the U.S. we use psi. And I've seen some have an operating pressure, some pipelines have an operating pressure of 2,200 psi. So again, when it comes to operating costs, it is 100% correlated to the amount of carbon dioxide that you're capturing. There are a number of ratios that you've got to pay attention to in your projects. The steam ratio, some solvents require less heat to release the carbon dioxide, others require higher temperatures, therefore there's going to be more steam use per ton of carbon dioxide captured. There's power, how much solvent, which is in many cases at least half water. You're moving these fluids around back and forth, and the water is just there to facilitate the movement of the solvent and doesn't do any work, but you have to do work to move it back and forth. Solvent consumption, this is a two-prong issue. First, the solvent is expensive, and when an impurity makes it into your system and causes the solvent to degrade to the point where it either is unusable, it is bound up and won't capture carbon dioxide, or it volatilizes and goes out the stack. Either way, it's lost solvent. So that's a cost to your system, but more importantly, it's also an emission, whether it goes out as a spent solvent stream that has to be disposed of properly, or if it goes out the stack, it becomes a VOC emission. So both of those things cause cost, and you have to deal with these to make the system acceptable. These systems use a lot of water, and there's just a number of other metrics that people look at when they're looking at carbon capture systems to decide whether the economics are going to work. All right. So as I mentioned earlier, geologic storage is the means of disposing of the large volumes of carbon dioxide that the world is grappling with. Maybe other technologies will come along for disposing of carbon dioxide, but both of these, as I mentioned earlier, are the means for getting CO2 permanently out of the atmosphere. The saline formations have been demonstrated secure. We have a very rigorous permitting process in the United States called Class 6. It's a well design and well construction, materials of construction specification by the government. It also includes a rigorous monitoring program that includes monitoring wells, seismic, logging, core samples, many pressure monitoring, all kinds of monitoring that is necessary to ensure that the CO2 as it's injected into this formation is going to stay there and not affect the integrity of the formation. Enhanced oil recovery is in the United States a Class 2 injection process. It has been going on in the U.S. for over 50 years. There's never been an accident where people got hurt. There have been in the 50 years and the thousands of wells that have been involved, there have been 2 wells that have had issues. So that's a pretty good track record. And during those issues, there was no groundwater contamination, and there was only a minor amount of carbon dioxide that was released before the wells were brought under control. That's the magic of these mostly sandstone, some carbonate formations, but the pore space has, I'm not an engineer, there's a capillary effect that tends to hold the gas and not let it move through the rock. It's a resistance. So if you somehow had an open well bore into the formation where you've been storing the CO2, it's actually very slow to move back to the well bore and try and escape. We've done the modeling on it. There's been some tests done in West Texas to prove out the concept. So most people, when they think of a reservoir in the ground, they think of a big cavern, and you've got this big bubble or pool of carbon dioxide that is just sloshing around waiting for a leak to get out. But in fact, these formations act more like your kitchen sponge on your kitchen sink. You can think about how hard it is to get the water to come back out of a sponge. You've got to do a lot of things to it, and even then, it's really difficult to get all the water out except air drying, right? Well, the same thing is here. These are very small pore spaces, and it's very difficult. I think most people would tell you it would be almost impossible. Even if you wanted to cause the CO2 to come back, it'd be very difficult to make that happen. So I don't know if any of you have read articles that have been written about the Petronova project. You can Google it. There are people in the world who are opposed to fossil fuels of any kind. They use the carbon emission aspect of fossil fuels as the reason that they're opposed to them. And so when carbon capture and sequestration, CCS, comes along, you would think they would be happy. We now have a way to prevent the bad aspect of fossil fuels from impacting the environment by capturing carbon dioxide. But for these people, it's not about carbon emissions. It's about fundamentally shifting energy sources in the world. So when we find a solution like CCS, it still meets with resistance because, for one thing, the last thing that group of people wants to see is coal to be acceptable environmentally. It just drives them crazy. So there have been a number of articles written. The Petronova project ran for 3 years for a demonstration. And then because oil prices were low in 2020, right at the beginning of the pandemic, the owner of the plant elected to shut it down. And so because it was shut down after only 3 years, a lot of articles were written about how it was not successful. And I'm helping many companies in the United States think about their carbon capture projects. And one of the first questions I always get is, well, the Petronova project, it got shut down. That proves that it didn't work. There's many articles written that it didn't work. Well, that's a uninformed opinion, because the Petronova project was an oil company. When I developed that project, we didn't have government incentives to make that project work. I had to find a way other than just raising the cost of electricity to our customers, which they would never accept. And in the market that we were operating in Texas, customers have a choice. They don't have to buy from you. If your price is high, they will go to somebody else. So it was not an option for me to just say, well, we're now capturing carbon dioxide, so we need to raise your price of your electricity. Customers would say, no, I'm out of here. I'm going to brand X next door. So I found a way to create a project where we bought an oil field, because the amount of oil that can be produced by putting carbon dioxide in an oil field, that incremental amount of production could not only pay for the cost to prepare the oil field for CO2, it would also pay for the 80-mile pipeline, I guess 120-kilometer pipeline to deliver the carbon dioxide, and the construction and operation of the capture system. There was that much incremental oil in this field to be had. So Petronova was an oil company that had embedded in it a CCS demonstration. When the oil company decided that it needed to shut down because of oil prices, it had nothing to do with the effectiveness or the operability of the CCS system. So here's a look at what that project looks like, that carbon capture project. On the lower left, you can see the round flue duct. This is coming from the power plant. And by the way, the perspective here, this picture was taken from the top of the stack, the exhaust stack of the power plant. And so the flue gas comes in. That first vessel that you see there is the quencher. This is where we take the temperature down so that the CO2 will stick to the amine whenever it makes it into the next vessel, which is the largest one there. The label for it is in the upper left there, is the absorber. This is where the flue gas is mixed and the solvent is dripped or coated on packing. And so as the flue gas bounces around in there, it comes in contact with the liquid amine, and the CO2 is caught in the amine. The amine is collected in the bottom of the absorber. It's full of carbon dioxide. The solvent is very expensive, so you don't want to just use it once. So we move that CO2 laden solvent over to the regenerator, which is that next silver bullet next to the absorber. And in here we heat it up. The CO2 comes out of solution. This process is so selective that it actually makes food grade CO2. So you'd have to do a little bit of cleanup to make sure that there weren't any carryover, but it's 99.9% pure CO2 coming out of this process. Then we have the compressor, which is nestled in right behind the absorber. Take the pressure up to, in this case, it was 1900 psi. Supercritical, that's where CO2 acts like a liquid, but it's still considered a gas because it's still compressible. And then you can see the very beginning of the CO2 pipeline right behind the unit. As I mentioned, in this market, it was not going to be possible to raise the cost of electricity. And if we had gotten our energy from the power plant, it would have raised that unit's cost to make electricity, irrespective of the cost to capture carbon dioxide. So we built, in this case, because of the mandate to not raise electric cost coming out of this unit, we built our own cogeneration system. And again, this was a CCS demonstration. It wasn't intended to be a compliance unit where we were complying with greenhouse gas regulations or permits. This was simply to demonstrate the technology. And so the best way to get that done for us in our situation was to put in a gas-fired combustion turbine cogeneration system to make steam and electricity to power the carbon capture system. In the follow-on projects, and this was fully disclosed as we did this demonstration, it's really expected that you will find a way to use the host power plant or the host petrochemical facility to provide your steam and power for your carbon capture system. I'm consulting on 6 different FEED studies for carbon capture projects in the U.S., and all of them are going to be using the host source for their electricity and their steam. That's significant because the parasitic load, the energy needed to capture carbon dioxide, is an emission source for carbon of itself. And so if you're pulling those 2 energy sources from a unit that already has carbon capture on it, by definition, you're capturing the carbon associated with what's called the parasitic load for capture. So, as I mentioned, it was constructed on time and on budget. This is very significant. There have been a lot of spectacular failures, spectacular failed attempts to show carbon dioxide or prove carbon capture, not only in the United States but around the world. And so this one, though, we were able to get it done on time and on budget, thanks to a very well planned and orchestrated construction effort. Mitsubishi was the technology provider. They were just, to use our vernacular, they were lights out. They knew what they were doing. They were teamed up with a U.S. construction company called Kiewit, and the team together just executed almost flawlessly, and that's despite many, many challenges along the way. The compressor had problems during manufacture, and it's the longest lead item in the construction and threatened to make the whole project late. And they worked and actually shipped the compressor via the Antonov to avoid the 4-week shipping time by water. The regenerator, the vessel where we recover the CO2, was manufactured in a shipyard in South Korea. And halfway through fabrication, the shipyard went bankrupt. And so we had to, in the middle of the night, find a shipyard next door that was willing to finish the work, move it over there, and then get it shipped on time, which they were able to do. Let's see. We had one day during the construction where the site received 1 meter of rain in one 24-hour period. And so that took days of cleaning out to recover from that. So we just had a lot of challenges along the way, but despite all those things, we were able to come on time and on budget. The reason Petronova is not operating is the oil side, the oil production side, just didn't pan out commercially like we thought it would. First of all, we were expecting an incremental 10,000 barrels per day production from oil injection. And you can look, it's a public record, you can look on the Texas Railroad Commission, which it's a weird name for an oil regulation entity, but they regulate oil and gas production in Texas. You can see that they never got more than about 5,000 barrels a day, which was pretty devastating to the economics. And then also, at the time that the project was approved by the boards and the lenders, oil was at $110 a barrel. In our pro forma, we had assumed $60 per barrel. And by the time the 30-month construction period had ended, oil was at less than $30 per barrel. So half the production, half the price results in some pretty challenging economics. And then finally, I just want to point out that by the third year, yes, there were some technical things that had to be worked out. Anytime you do a 10x scale up of an industrial process, you're going to find things, you're going to discover things. And the first couple of years, we were at about an 80% capacity factor. And in the last year of the demonstration, we achieved greater than 90%. So that's pretty successful for something that's never been attempted at this scale before, especially when you consider many of the other projects that were attempted in carbon capture, some gasification technologies and some other folks that were trying to do things were way over budget and never came online. Okay, this is nearing the end, and I just wanted to kind of give you a relative sense of what the cost of carbon capture are. Ethanol producers, you know, it's very popular in the U.S. It's considered very carbon friendly to burn ethanol in gas tanks, in vehicle tanks, fuel tanks. And you can see that the cost to capture carbon dioxide off a ethanol digester is in the neighborhood of around $30 per ton of CO2. In the United States, there's 2 programs that are available to ethanol producers to incentivize investment and operation of carbon capture on these units. One is 45Q tax credits. You'll hear that 45Q bounce around a lot if you talk to any CCUS developer. That's $50 per ton. And then California, if you can get your ethanol to California from wherever it's produced, they will pay $150 to sometimes as much as $200 per ton for that low carbon fuel. So very profitable and there are many ethanol plants that are scrambling to put carbon capture on. Their biggest challenge is their volume of CO2 produced is much smaller than at power plants. And whenever you're talking about building infrastructure, you need lots of volume in order to amortize down the cost of pipes and transportation and storage. So right now what's happening is there are groups that are consolidating groups of ethanol producers to try and amalgamate enough volume to justify a pipeline, because unfortunately most of the corn production in the United States is not near favorable geology for CO2 storage. So where the ethanol producers are, we need to gather them together, justify a pipe that runs about 200 to 300 miles to an area that has acceptable geology for geologic storage. So they need every bit of that $200 per ton incentives to make it work and still have an economic return for the project. On the right-hand side, I got an example of a coal-fired power plant CCS, and it is the numbers that you see here for capital and O&M come out of a study that was done by the National Petroleum Council, and they think that it's about $100 per ton to capture carbon dioxide on average for the average coal plant in the United States. And you can see that right now the incentive is only $50. So while there's many studies going on, we will see very few projects unless the incentives are increased. One such project I list here called Tundra is actually close to $50 because it sits right on top of its storage. So there are a few projects that will get done at $50, but as this graph shows, more incentives are needed if we want more projects in that sector. And that concludes my discussion. Thank you.